Okay, so you guys should be working on. Sorry for not being there today. My wee boy's got a cough, so we had to get him tested. And I know it's a bit naff of me to put pressure on you guys to attend, and then I don't show up the very next day. So yesterday we were doing electronics recap. I had set up a quiz with 5 questions in it. Make sure you put your answers into that quiz. What we're going to do today is we're going to talk about logic. Now, just a really quick reminder, very, very quick. So, of the National 5 content, those are the 3 functions at National 5. Those are the 3 gates at National 5. And then we could talk about the Boolean terms. That would be B, sorry, Z, A, B, Z. So the Boolean term for that would be Z equals not A, Z equals A and B, Z equals A or B. And then we should be able to do a truth table. I'm not going to go into the detail of a truth table or how we construct it, because that is National 5, but that's what the truth table for the NOT gate looks like. The truth table for the AND gate, this is stuff that's not in the data book, so you really need to try to remember this stuff. So for an AND gate, Z will be on when all of the inputs are on, will be off in all other cases. And then for an OR gate, Z will be on if any of the inputs are on. So that was National 5 kind of basic content. We added some gates in it higher. The gates that we added in it higher were the NAND gate. So that N stands for not and. It was drawn like that way, a circling in just the same way the inverter is. So it's almost like an AND gate with an inverter inside it, not and. The Boolean term would be Z equals A NAND B. Notice the bar goes right across the inputs and the sign. And the truth table for the NAND gate is the opposite of the truth table for an AND gate. There's AND, so that means an AND is not that. Let me introduce you to the NOR gate. So kind of same deal. It looks like an OR gate except it's got a circle on the end. Its Boolean term is Z equals A NOR B. So notice the bar goes across the inputs and the symbol for the gate. And the truth table looks like this. So it's the opposite of the OR. Whatever the OR is, the NOR isn't that. And then the last one we introduced you to was the exclusive OR gate. It's called an exclusive OR, sometimes abbreviated to XOR or EOR. Symbols got the double line there, A, B, Z. The Boolean term is A, X or B, so you put the OR sign inside a circle. And the truth table is the same as the OR, but it excludes, this is why it's called an exclusive OR gate. It excludes the entry where all of the inputs are on. So it excludes that one. That's a 0. So those are all of the gates that you need to be able to recognise and name and work with at higher. Okay. Sometimes this in the NOT gate is called an inverter. And the NAND gate can be referred to as the universal gate, because you can use the NAND gate to model every other gate. So what kind of skills are you going to have with this? You're going to have to be able to extract a Boolean term from a circuit. Okay, so we're looking to end up with a Boolean term but for a combinational logic circuit. So you might have a circuit with lots of gates in it. So let's go A, B, C, D, Z. And you're asked to arrive at a Boolean expression for Z. Some people will just be able to look at it and do it, right? So, just working from, top left down to Z. So it's A and B, nor, not C, and D. So some people can just do it by inspection. A and B, and that's a gate. And that's not ORed with not C. It's a function on its own, and that's NANDed with D, and that's a big gate on its own. So you can arrive at that by inspection if you wanted, if you're good at that. The other way to do it is to label your intermediate signals. So that would be signals that are neither input nor output, signals that go from gate to gate. Like this guy, he's an intermediate signal, let's call him E. And this guy's an intermediate signal F. And this guy's an intermediate signal G. Write down the Boolean expressions for them. So E equals A and B. F equals not C. G equals E nor F. E nor F. And Z equals G and D. Yeah, and then just start, because we've got Z but not in terms of inputs, G's an intermediate signal, so that wouldn't be an appropriate answer. Just start substituting the intermediate values in. So whenever you see a G, write E nor F instead. So we would go Z equals, so instead of the G, we'd have E nor F. Nothing else changes though. That's still NANDed with D. Make sure you get your brackets right. And E and F still aren't inputs, they are intermediates, they need to be substituted out as well. So F is not C. And E is A and B, right? So let's say wherever we see an A, we should have an A and B instead of the E. That's still getting NORed with F, but F is actually not C. And that's all NORed together. And then that's still getting NANDed with D. So you can see how they two are the same. That's one of the skills you need to have. And then the other skill you need to have is to be able to use your knowledge of the NAND gate as the universal gate. So all those individual NAND equivalences you'd need to be able to put in place. So just as a recap, but incidentally before I move on from this page, that's two different ways of doing it. One just by inspection, and then one by naming the intermediates and substituting them in, okay? Right, so NAND equivalence then. So for NAND equivalence, you should be able to go not and or NAND nor and the exclusive or. You should be able to draw a gate or a network of gates that does the job of all of these individual gates. So how do you make, and again, this stuff isn't in the data book, so you're going to have to remember it. There's the originals. How do we use the NAND gate to model a NOT gate? So you have to remember, and this is the kind of key one. This is the one that kind of underpins most of them, right? If you take a NAND gate, and again, this is recap, so I'm not teaching it. If you take a NAND gate and tie its inputs together, that will operate as an inverter. Because if you think, again, I don't want to waste time teaching it. See, waste time teaching it. Yeah. So there's the NAND gate there, right? If I've tied A and B together, that means I can only ever have both inputs as 0 or both inputs as 1. Yeah, I can only ever have that line or that line if I've tied the inputs together. Can't have the inputs as different values. I can only ever have both 0 and both 1. If they're both 0, the output's on. If they're both 1, the output's off. So it's operating as an inverter. If I provide a red signal here to both of them that's off, the output will be on. So that's the basis of how a NAND gate operates as an inverter, looking at the truth table. Sorry, I realise I'm a bit low there. Okay. And then the rest of them are just circuit equivalences. It's kind of, maybe, hopefully, if you want to use NAND gates to make an AND gate, hopefully you realise that it becomes a NAND with another inverter on the output, because remember, so that'll give you an AND function, because that's a not AND. That's already Z equals A NAND B, and then what we've done by putting this on it is we've put another bar on there. That's a double inversion. Double inversions can just be ignored, so that's the same as A and B. Okay. Obviously, we don't need to worry about the NAND equivalence of a NAND gate. Now an OR gate. Now, if we take, I'm kind of running out of space here, I'm going to have to go down here. That's that one. That's that one. Right, so down here, if we take a NAND gate and invert its inputs, and I'm only going to use NAND gates. There's a wee NAND gate there, inputs tied together. So a NAND gate with inverted inputs operates as an OR gate. You just need to take that as gospel. You could do the truth table for that if you wanted to prove A, B, Z, A, B, we've got intermediate signals, C and D here. C and D, and we've got our output Z. C is not A, D is not B, and Z is the NAND of them. If I put that into an AND gate, I would get on, so I get off. If I put that into an AND gate, I would get off, so I get on, off, on, off, on. Yeah, so the truth table for that system reads that, which is exactly the same as the truth table for an OR gate. Don't know why I feel the need to try to prove this stuff to you. So then it would follow that if you want the NAND equivalence of a NOT OR, you would take that and invert the output again, just exactly the same way as we were doing. So it's an inverter tied together, sorry, a NAND gate with its inputs tied together, there's A and B, into another NAND gate, and then invert that output. So that bit there functions as an OR gate. If we invert the output, it functions as a NOR gate. Last one's the exclusive OR. I would ask that you basically go through like the reverse process. It's a skill that we do cover, where you actually go from a truth table to a circuit. If you can't remember this, okay, so the truth table for this guy is the key to figuring out what the NAND equivalence is if you can't just remember it. Right, so the truth table is that. You should be able to get a Boolean term for Z from the truth table. So we're looking at this entry here, because there's a 1. And there's another 1 here, so we're looking at this entry. So it's that or that gives us a 1. So Z equals not A and B, or A and not B. And then you can just do the circuit for that. So you've got A, B, inverted into an AND gate, into an OR gate, and then you've got E and, so you get another AND gate, the OR gate, and that's your Z, and this needs to be, bring that down to the bottom, like that. So that's your not A and B, that's your A and not B, that's the all together to give Z. Then you would do the NAND equivalence of this circuit. So the NAND equivalence of this circuit, we've got A in that space, and B, so you've got the inverter going to an AND gate, and you've got this other AND gate, so we've got the inverted B, the non-inverted A, and then go to an OR gate, so that's inverted inputs. There's a double inversion there, so the two can go, and the two can go. So that leaves us with this a kind of a very messy proof of what we've been working through here. So that's going to leave us with, make sure you guys can see that. Can't really see my camera screen, so I don't know if that's all the way on there or not. That's your NAND equivalence of an XOR. So if you did the truth table of that, you would find it would be the same as an exclusive OR gate. Okay, so that's the NAND equivalences of all the gates. That's XOR. There's NOR. There's OR, there's and there's not. So draw your attention to them in case you want to pause this and sketch these out again. The last one's there. So you need to be able to put those identities into other circuits. So let's do a quick example of that then. I'll leave that on that page. Right, okay, so if you've got, what was our original circuit for that question earlier on? Let's use that circuit there. So it's A, B, C and D. A and B go to an AND gate. C, and that going to a NOT OR gate, and that going to a NAND gate. Okay, so let's say we're asked to do the NAND equivalence of this circuit. Remember, the reason we do NAND equivalence is to try to reduce the number of gates, but specifically to try to reduce the number of chips, because all of these gates here, see these gates, if you look at these, it's a kind of horrible thing that the gates, the actual practical part of it, isn't necessarily part of the course anymore, but NAND equivalence is. So the AND, the OR, the NAND, the NOR, and the exclusive OR in their two input form, they're supplied in little chips that have got 6 AND gates in them, 6 OR gates, it's 4 AND gates, 4 OR gates, 4 NAND, 4 NOR. So if you're using one AND gate, then you've got a chip with 4 AND gates in it and you're only using one. There's a lack of efficiency there. The inverters are supplied in chips that have got 6 inverters on that chip, so if you only need one inverter, there's 5 gates that you've had to buy and supply and that you're powering in your circuit that aren't getting used. So this is why we use NAND equivalents, because we can remove all those other gates. We can make our systems much more efficient. So as things stand right now, this circuit here is going to have 4 chips on it, and it's going to have, you know, if I just take a note of this, you don't need to be able to do this, I don't think, right? But you still need to justify why we do NAND equivalents, maybe without the numbers, right? But I just want to kind of get it in your head. So there'll be 1 chip with 4 of them on it, 1 chip with 4 of them on it, 1 chip with 4 of them on it, and 1 chip with 6 of them on it. So we would have 12 plus 6 is 18. So we'd have 18 gates in the circuit in total, but we're only using 4 of them. 4 chips, 18 gates. Let's do an equivalence and then work out what we end up with there. So we're still going to have A, B, C and D as our inputs. We're going to replace that guy with the NAND equivalence. Oh, so we've actually added a gate in there. I think, well, that's not very efficient. A NOT OR gate. Added loads of gates in there. We've got an inverter down here. It's handy to try keep track of how many overall gates you've got, you know what I mean? That's another one down there. Yeah, different colour. Drop my green pen. Don't know where my green pen is. And then we've got this NAND gate. So the NAND equivalence of a NAND is just a NAND. Fantastic. Okay. What we're going to do then is get rid of any double inversions. So we've got a double inversion there, got a double inversion there, so we can get rid of all 4 of those gates. Now in an exam setting, you're okay to just to do this. Strike, 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 strike. You're okay to finish there. I'm just going to redraw it with those gates missing, just for the full effect, make the count easier again. So we've got now a NAND gate. What's all missing? It goes to another NAND gate, which is an inverted output. And goes to another NAND gate. Right, so believe it or not, this circuit will behave logically exactly the same as this circuit. Right, you don't need to believe it. You could build it in Yanka and check it, or you could just draw it out and then do your truth table and name your intermediates and build a truth table for it to prove that they're exactly the same. But then have a look at the chip count. Remember, there's 4 of them in a chip. Now we're only using NAND gates and we're only using 4 of them, so we're now at 1 chip, 4 gates, 100% utilisation. No unused gates in the circuit anymore. Much more efficient. It also means that if we follow this procedure every single time, we only ever have to buy NAND gates. We wouldn't have to keep a stock of any other gates. So that's quite handy. Okay, so that's NAND equivalence. So that's your recap of logic of the different gates. This is the higher content that was added in from National 5. The base level of skill that you have to be able to do is, and demonstrate, is that you have to be able to strip a boolean from a circuit, and you're going to have to be able to create a NAND equivalence of a circuit showing simplification. Right, so wherever there's double inversions, getting rid of them. Only where there's an inverter followed by an inverter, because remember, that's the whole thing about double inversions. If you invert an on, you end back up at on again. If you invert an off, you end up at off again. Sorry, if you double invert an on, you end back up at on. If you double invert an off, you can back up it off. So the double inversions can just be completely removed. Don't ever, I wouldn't go down the road of trying to simplify Boolean expressions. People will make mistakes and it's not a skill that you need to have. So like down here, I did talk about it back in the day where you can break the line and change the sign. So, you know, if you wanted to simplify this thing here, you could break that line and that would leave you with that. Which means you could ignore that double inversion, which would leave you with that. Which looks a lot nicer. Oh no, that's not, that would be an or in there, because we broke that line and changed that sign. So yeah, I mean, those are processes you could do, but you're not asked to be able to simplify Boolean terms like that. But you are asked to simplify circuits after NAND equivalence. Okay, at this point I'd like you to find the logic past paper questions and do as many of them as you can. Hopefully this only takes up the first of the double period and I'll do another video for the second period. Thank you.